Welcome to the state symbol lesson. So I've been talking about how I'm going to show you this, I'm going to show you this, so here it is now. So there's a lot of states that you should already be comfortable with now, but I'm going to show you a few more today and then just get you to practice with some of the concepts that you've already covered where you're predicting the products of different reactions. Back in Unit 1, I gave you guys this diagram here of the general states at SATP, so standard ambient temperature and pressure. So fancy way to, in general, to say, like you could think of it as like room temperature. At room temperature, if you were to find a piece of calcium on the ground, it would be a solid, okay? So that's all the kind of the light purple here. And then you have a couple blue ones here where it's mercury and bromine. Those ones are liquids, okay? Those are the two liquids. And then we have the orange here that these are the gases, okay? So, so back in Unit 1, I wanted you to memorize that. So on a periodic table, we have mercury and bromine, that are liquids, and then we have hydrogen gas, right? Nitrogen, oxygen, fluorine gas. Chlorine was used in the war, so that's a gas, and all the noble gases. Okay, so just all the noble gases, and then we have like the FON here, okay, chlorine and hydrogen. So those are all the ones that are gases. So make sure if you've forgotten to get those memorized so that today when you're writing them in chemical reaction equations that you're writing gases for those. Metals, you are writing just solid, and then whenever you see mercury or bromine, you're going to write liquid. So if you ever have the individual elements in your chemical reaction equation, so here are some notes here. So again, I told you like to write the different state symbols. So here are the state symbols, like solid, okay, in brackets, and it's a subscript. Okay, so like it should be a subscript like that. And liquids are L, okay, gas G, and then aqueous. This is where if you've taken a substance, mixed it in water, so now it's a solution, you're going to say the state is aqueous, so AQ. All right, so if we're looking at the individual, just if it's just an element coming in or in the reaction, so most are solids here. So if you take a look here, it's all light purple, the majority of this table. But there are exceptions, right? So I said mercury and bromine, remember, memorize those. Those are the gases. And iodine, okay, is a solid, okay? And all the noble gases are gases. And then we have our super 7 here, the Hofbrinkel. So I wanted you to memorize Hofbrinkel because this is the way to memorize all the ones that are diatomic. So whenever you have a hydrogen, any of these in a chemical reaction equation, they should be diatomic. So it should be H2N2O2, okay? Cl2Br2I2, okay? On top of it, the Hofbrinkel, most of them are gases, but there are the two exceptions, bromine, right? So that's the liquid, and iodine here, of the diatomics, is a solid, okay? So you just got to get these memorized, practice them, and as you do lots of questions, you'll get them memorized, right? But for now, you know these two are liquids, and most of them are solids, and with the diatomics, though, they're all gases except these two. Okay, so there are some other notes that I want you to, again, just as you do lots of practice, you'll get these memorized as well. Okay, so the acids. So when we started naming the acids in IUPAC nomenclature, it was always like you write the metal. Like, for example, IUPAC is like if you have sodium and chlorine, you say sodium chloride, okay? So whenever we had an acid like HCl, we would write aqueous hydrogen chloride. So we were always writing aqueous, but I didn't pick on you if you weren't doing it in the nomenclature or the naming assessments. Okay, so now though, I want you to, but most of you were writing them in your assessments, so that was good. So I want you to now, whenever you see an acid, so most of them start with an H, right? So yeah, all the ones you'll study, I guess, this year start with an H. So you're going to find that anytime you see that in a chemical reaction equation, you want to be writing AQ as the state. Okay, so here I'll just write some examples in here. Okay, so we have HCl. Okay, so you see the hydrogen there, and then you have the chlorine ion. So this is hydrochloric acid, or it's aqueous hydrogen chloride. Okay, so with the classical name hydrochloric acid, you don't need to write aqueous, like say the word aqueous with the name, because just when you say hydrochloric acid, they know that it's the liquid, it's the aqueous form of that acid. So, but for the formula though, you need to write HCl and then subscript AQ, okay, to show that it's aqueous. All right, so another example like sulfuric acid, okay, or aqueous hydrogen sulfate. Okay, so there. So anytime you see an acid now in a chemical reaction equation, you can just write AQ. Okay, now we'll move on to water. So water here, so it's a pure substance, right? It's you would say it's a mixture if I take water and say I take, hydrogen chloride and mix them together, okay? Or if I take sodium chloride, salt, and take water and mix it together, then it becomes an aqueous solution. But if I just have water in my chemical reaction equation, it's a pure substance, and at room temperature, water is a liquid. So we would write the little subscript L. Okay. The only exception is if you have a combustion reaction. So if you have those hydrocarbons, so it's like a compound of carbons, hydrogens, or carbons and hydrogens and oxygens. If you have one of those, one of the fuel type questions where it's burning an oxygen, you're going to get a combustion reaction. And in that case there, because it's burning, you're going to have the reactants and products all in gaseous states. The water here will be gaseous, okay? So we'll look at the combustion reaction a bit more in a sec, but so you're going to have water will be gaseous in that example, okay? Because if it's a complete combustion, so if I just write an example here, if you have a complete combustion of, I don't know, like methane here, okay, so it's burning an oxygen. And then you always get the two products, so we're assuming complete. We always get the carbon dioxide product, and then we always get the water product. Okay, so what will these state symbols look like? Okay, so this will be gaseous. That's gaseous. I should have left a bit more room for the subscript. So make sure you guys are doing this too when you are writing chemical reaction equations today and balancing. Leave space in the front so you can balance. Leave space after so that you can write the state symbols in. Okay. All right. So so methane was gaseous. It burned in the oxygen and it produced, if it was a clean, complete reaction, carbon dioxide gas and water as a gas. Okay. So water vapor. Give that way. All right. The next one's here. If you wanted to look at, so whenever you are dealing with a metal oxide, so think of it like if you left a metal out in the air, just exposed to oxygen, what would happen? It would rust, okay? So, and then what state is rust? So it's solid. So here we can write a little note. Think of this one as being like rust. If you have a metal oxide, it's like you have rust. Okay, so if you have rust, you have a solid. Okay, so an example would be like iron oxide. So iron 3 oxide. Okay, so if you have a metal oxide, you would have a solid like that. Okay, so anytime you see a metal oxide compound, so magnesium oxide, iron oxide, copper oxide, just write solid. Okay, and then the way to remember it is just think it's the rust. You left the metal out, it rusted, and rust is still solid. Okay, and move on to the next one, which is non-metal oxides. Okay, so you're thinking, okay, what is that? What's an example of a non-metal oxide? So if we take a non-metal and combine it with oxygen, okay, so think of it like carbon. Carbon is a non-metal. And if I combine it with an oxygen, okay, I get carbon dioxide. So at room temperature, what state is carbon dioxide? Well, it's in the air. It's in the air, right? So, and we know it's gaseous. Okay. What if I pick some of the other ones, like some of the pollutants, like Okay, dinitrogen tetroxide. Okay, so we have a non-metal with an oxygen, right? Compound, the same thing, gaseous. Okay, on to the next one. Combustion reactions produce carbon dioxide, water in their gaseous form. So I already covered that. It's just right up there. Okay, so just refer back to there. Okay, so yeah, so just carbon dioxide and water. Well, water will be vapor, right? Carbon dioxide will be gaseous. Um, so whenever you have a combustion reaction, then know that you're going to have gaseous products like that. Okay, if it is a incomplete combustion though, so maybe we should write complete combustion reaction. Okay, if it's an incomplete combustion though, you're going to get gaseous products, but there will be one solid product that I'll show you in a video. So watch the combustion video. So you're going to find that there's some soot that will appear, and that's a solid. Okay, but otherwise everything else is gaseous. Okay, now onto the single displacement reactions. So what we were analyzing with these reactions was one metal would come in and displace a metal if the metal was up higher on the activity series, or a non-metal like a halogen would come in and displace another halogen again if that halogen is higher up on the activity series. So whenever we did that, we would always get a compound of a metal and a non-metal coming together, so an ionic compound. So in these reactions here, for these reactions to take place, we would take, say, like we go to the cabinet and we get some of the, I don't know, like we get iron and then we get aluminum chloride powder. So we'd have to mix that aluminum chloride in water and then dump the iron in, and then we get a reaction happening. So this all has to kind of take place in water. So the ionic compounds that are involved in these reactions are aqueous. Okay, so for example here, let's write in, so let's say like iron comes in, okay, and say we're reacting it with nickel chloride, I guess. Okay, so I'm just picking one that's going to work here. Okay, so nickel 2 chloride. And so you're going to find that, yes, iron is higher up on the activity series, so it's going to displace the nickel. And then let's just assume it's iron 2 chloride. Okay, and the nickel will be displaced. Okay, so there is our example of a typical single displacement reaction, and I am going to go through here and now add the state symbols. So again, a reminder, you know that whenever you have a metal in the reaction equation, you just write Fe. Don't write the charge, don't write a subscript, it's just Fe, okay, just the element. So then, and then you know that iron is one of the metals, so you know it's always, like if you found it, it would be a solid, okay? All right, and nickel chloride, so we would have had it as a solid, but then for this reaction to happen, we would have mixed it in water. So any ionic compounds, just change it to aqueous. All right, and then we have iron chloride, same thing. So now it gets displaced. This new ionic compound is aqueous. And then the metal that got displaced, now it's just sitting there in that solution as a solid. Okay, so whenever you have a metal just on its own, solid. Okay, so for a single displacement reactions, the product that's formed, that's ionic, is usually aqueous. But what you're going to do is you're going to use your solubility table that we looked at the other day and determine for sure if that's the case, okay? So yeah, any ionic compounds that are coming out, just use the solubility table. So in this case here, iron 2 chloride is aqueous because chlorine, when it's combined with certain metals, it does form a precipitate, but in this case, iron, it's okay. Okay, so again, I know there's a lot of stuff here, but we're just going to practice lots, and then we'll, hopefully by the end of this lesson, you'll feel confident finding finding not only the products that are formed, but the states that they're in. And on top of it, we're going to practice some balancing as well today. All right, move on to double displacement reactions. So, so what we had studied here the other day was that we would bring in a couple ionic compounds, we'd mix them together, okay, and again, I just said, okay, go with the assumption the reactants are aqueous, so say we took the powder of this one and powder of that one, mixed it in water, and then we dumped it in together so that a reaction can happen here. And then from there, we had to determine if the products that were coming out, if there was any precipitate, so if one of them became a solid, or if not, then would they both stay as aqueous. So if you look here, so again, I just wrote down, okay, so the reactants, what you start with, aqueous, okay, and then we know how to check for the precipitate now. Remember using that solubility table in the back of your periodic table. And the other one is usually aqueous. But, you know, there are some reactions where they are both come out. And yes, you get two precipitates that can come out. So anyway, just check the solubility table. So I'll just write here, okay. Remember to use the solubility table. Okay, so let's just do get an example going here. So I'm just going to go, I don't know, sodium chloride and silver nitrate. Okay, and then leaving space here. I'm not going to balance these right now, but I will in the example. The examples that we do. But for now, just state symbols, concentrate on. Okay, so we have an ionic compound, sodium chloride, and we have another ionic compound, silver nitrate, coming in, and you're going to get a double displacement reaction here. Okay, so I picked these ones because they're nice and they all have a charge of 1. So they just swap places. So the sodium is now with the nitrate, and the silver is now with the chlorate. Okay, so now that we have our products there, I want you to go through and determine the state symbols. So again, I said, all right, so any of the ionic compounds you start with aqueous. So just say you took some salts from the sodium chloride from the cupboard and you mix it in water, make a solution, aqueous solution, and then take some silver nitrate, mix it in solution, and then you're going to dump them together and observe the reaction, and you're going to find that sodium nitrate forms. So if we look at our solubility table, okay, so we're going to take a look at our solubility table. Here it is. So we're looking here at this box here. So we have sodium nitrate. Okay, so we're looking at box 1. Okay, so remember anything that is a group 1 metal or is combined with a group 1 metal, sodium, it's going to be aqueous. Okay, so I'll dissociate. So we know that this first one here, again, I didn't leave myself enough space, so just make sure you guys have it in there so that it's right beside the subscript 3. Okay, and then the other one is sodium chloride. So again, not sodium chloride, it's silver chloride. So I'm looking here, I don't see silver, I don't see chlorine, so I'm going to go to the next box here. Oh, there's chlorine, okay. And if you look at silver here, it says that with chlorine and silver together will always form a precipitate. All right, so back here, then you're going to go back and assign silver chloride a solid state symbol. Okay, so there's a lot now going on here. You need to be able to predict the products. You need to predict the products that'll form by understanding, oh, is it a double displacement? Is it a single displacement? Is it a combustion reaction? And so forth. And then you have to write the state symbols. You also need to be able to balance. So there's a lot of stuff that is expected of you now, and you should be able to do those with confidence, okay? If not, remember, just keep practicing every day. Just because you finish one lesson, you can still go back and kind of practice the other ones, and always check your answers to make sure you're on the right track. Okay, yeah, so again, the rule of thumb, the reactants just make them aqueous, but then the products, pay attention to the solubility table. You can get both of them as solids, you can get both of them as aqueous. okay? But because there's like a ionic reaction, aqueous solution reaction happening here, it's going to either be aqueous or solid, just the ones we'll study, okay? Um, and yeah, the ones with gases, I know I touched on those. Don't worry about those. I won't give you ones like that. All right, so let's go to the last bit here. Okay, and this is kind of the same thing. So check the solubility of the salt using the solubility table. Okay, so that really should kind of go in there. Double displacement note. All right, so here is a summary of kind of what I just covered there. So you can kind of have this out, or if you prefer to have these notes out, then you can do that. The solids, so what you're going to find for the solids, basically all the metals, okay, on the periodic table, okay, except, remember the exceptions, mercury. Those will be solid. You know that anything that precipitates out using our solubility table will be a solid. Metal oxides, so again, remember that rust example. So anything like rust. So iron oxide is rust, but then you can still get other metal oxides, aluminum oxide, sodium oxide, okay, and so forth. Those are all going to be solids, okay? So just think rust is a solid. That's how I'm going to remember it. All right, and then iodine, yes. So I like to put that exception on because people think halogens are always gaseous, but they're not. They have like lots of different state symbols, like iodine's solid, bromine's a liquid, okay? Fluorine and chlorine are gases. So just put iodine on there just to kind of, yeah, just make sure you guys know that one. And liquids, okay, so we have the two on the here. So we have mercury and bromine. Remember, those are the ones to memorize, mercury and bromine, mercury and bromine. Okay, so mercury used to be used in thermometers. Bromine, if you look it up, there's brown, thick liquid. And water, right? Water is the pure substance. It's always a liquid state symbol. All right, gases. So we have the almost all of the Hofbrinkel, right? Okay, just not the bromine and iodine, but everything else here: hydrogen, nitrogen, oxygen, fluorine, chlorine. Okay, and all the noble gases. These ones here at the bottom, I know like this is an older periodic table, but like we've actually found these and they actually have names and stuff like that. But like assume that even this UUO, which is now called Ganeson, okay. Anyway, so those are all gaseous, okay, and then the rest here you can just assume that they're solids. So yeah, these are always gases. The noble gases are gases, and then the non-metal oxides. Okay, so remember these are kind of the new ones: metal oxide and non-metal oxide. So non-metal oxides, okay, think of it like carbon dioxide, right? So you're not carbon monoxide, okay. Sulfur dioxide, those ones are all gaseous. And yeah, whenever we're burning fuel, okay, think of it as it's all, super hot, and everything's going to be in a gaseous state, except when it's incomplete, when you're spewing out that soot and so forth, that's solid, but everything else here will be gaseous, okay? So the carbon dioxide, the water will be gaseous, okay? So here I know it said water is liquid, but here is the exception. All right, and aqueous, so again, the acids, okay, every time you see an acid, just write aqueous, but just know that like an acid would be gaseous, so they have to bubble it in solution, and then, anyway, so when we're using it in reactions and stuff like that, it's aqueous. Bases. Again, we're going to study bases a bit more, but if you're wondering what a base looks like, it's just like an ionic compound. But you'll see usually hydroxides, bicarbonate or hydrogen carbonate, or the carbonate ions. Okay, these compounds here are considered to be basic, and but yeah, they're just like typical ionic polyatomic compounds here. But anyway, so if we have to deal with those, they're going to always be aqueous as well. And so just in general, any kind of ionic compound that we see, we're going to go with aqueous. But remember, some of the ionic compounds, because it forms precipitate, you have to put solid state symbol. Okay, so hopefully now you have a little bit of confidence with state symbols. And as we're going through practicing more of predicting products, balancing equations today, you should be able to assign a state symbol onto your chemical reaction equations.